For question I, for 3I, we have the limit as n goes to infinity of n equals 1 to infinity of log n all squared over n cubed. Now, this one here is really hard to tell because we have this cubic function in the denominator, which we would expect to converge, but we have this ln n squared in the numerator, and it is a weak function. So we should kind of be thinking there's probably a pretty good chance it's going to converge. Now, we could probably guess at it converging, but there is a more formal test for this, and it's called the limit comparison test. Okay, so we can do this. We could take the limit as n goes to infinity, and we can compare this to a known converging limit. So I know that my basal series, 1 over n squared, is convergent. Okay, so if I can compare it to that and see what happens. And this limit comparison, what it does is, if I compare it to this, and I end up with a limit, okay, and we're going to see this test a little bit later on, but if I actually get an actual limit, I can say that the two functions behave the same. And so if one converges, the other one converges. So I'm going to say that, well, let's see what happens if it's behaving similarly to 1 over n squared. And I'm going to put it in like this, ln n squared over n cubed. And I'm going to see what happens. So I have the limit as n approaches infinity, and when I simplify this, the n cubes cancel out, so I'm going to have an extra n in the denominator, and I'm going to have log n squared, and what's that going to be equal to? When I plug in infinity, I get infinity over infinity. Well, that means I'm going to apply L'Hopital's. Okay, so applying L'Hopital's, I'm going to end up with 2 log n times 1 over n, all divided by the derivative of n, which is 1. Okay, and then when I plug in my infinity into here, I'm going to end up again with infinity over infinity. That n goes in the denominator. Okay, so then this is my limit here. I have again an opportunity to use L'Hopital's again. So limit as n approaches infinity, I'm going to get 2 over n, and this n in the denominator is going to differentiate to 1. Okay, I'm just going to maybe highlight that to make sure that this n here ended up in the denominator, which differentiates to 1. When I apply my limit, in this case, it's equal to 0. Okay, well, what I was really looking for was some limit. That means that they both behave the same. However, because it goes to 0, we can say that the numerator is weaker than the denominator. So we can say that this is weak, and then this is strong. And we know the strong function converges. That means the weak function must converge even more. So there we have shown by comparing it to the 1 over n squared with the actual test, we can say that this is convergent.